In this video, we're going to focus on simple regression, and we're going to see how we can find estimated linear regression. And we are going to also talk about the interpretation of the coefficient, linear regression coefficient. So for this, we're going to use data file Butler. So the difference between simple linear regression and multiple linear regression is that in simple linear regression, we have only one independent variable for predicting the dependent variable. So only one independent variable. So if we, if we want to explain the relationship between one dependent variable and one independent variable. So imagine take sales as your Y as dependent variable and marketing the dollar amount spent on marketing as your X. So marketing effort or marketing expense and sales. So if we want to write down the linear relationship, so that should look like this. So Y sales is equal to beta 0. Beta 0 would be the y-intercept plus beta 1 slope times X marketing expense, the dollar amount that you spend on marketing, plus an error term, which would be random, which would be a random variable. Right? So beta 0 and beta 1. So these are population parameters. These are unknown factors that are coming from the true relationship between X and Y. So these are unknown. And also error is unknown, but error is usually about other factors other than X that are not in this model. We haven't captured them yet in this model, right? So these are the factors. This is actually the variation in Y that cannot be explained by X. So there can be other factor other than the marketing expenditure that affects your sale, right? So you may have new product development that affects your sale. You may have experienced people or less experienced people, sales people, that may affect your sale. There might be some seasonality. There might be some market effect that this model does not include everything. Because of that, you will have some variation, right? So everything is not going to be explained by just X, by just one factor. Because of that, you will have some variability that we show it using error term epsilon. So moving on. So that was this actually characterizes, tries to demonstrate the true relationship between X and Y. And here we have two unknown parameters of beta 0 and beta 1. But what do we do now in order to be able to conjecture, in order to be able to at least find an interval estimates for beta 0 and beta 1? We're going to find the estimated line. An estimated line is going to look like this. Y hat estimated simple linear regression equation. Y hat predicted value of Y, estimated value of Y, estimated value of your sale in our example equals B0. B0 is now the point estimate for beta 0. Is the estimated y-intercept plus B1 estimated slope. This is the point estimate for beta 1 times the value of your X, the value of marketing expenditure in our example. All right, so now we have an estimated simple linear regression or estimated linear equation that explains y based on x, tries to explain y based on x. And I mean, this is just the point estimate, but this is going to be very much helpful in terms of explaining the true relationship between x and y. We're going to use this linear equation in order to be able to make some conclusion about the true relationship between x and y. But before that, it's very important to understand how we can capture this, how we can get this, and how we can interpret these B0 and B1, these actually sample statistic using our sample, all right? So if I want to summarize this whole process, so we have a population or true regression model, that explains the linear relationship between x and y, the true relationship, right? And we have the error term here. In order to be able to make some conclusion about this, these are all unknown parameters, beta 0 and beta 1. In order to be able to make some conclusion about beta 0 and beta 1 and the real relationship between x and y, we're going to take some sample data and come up with an estimated regression equation. We're going to use least squares method in order to find B0 and B1. So we find B0 and B1, and using B0 and B1, we are going to we're going to be able to estimate beta 0 and beta 1. We find point and interval estimate for beta 0 and beta 1 that helps us to make some conclusion about the true relationship between x and y. This is what we want to understand, right? Beta 0 and beta 1. So at the end of the day, when we're dealing with simple regression, the type of relationship, the direction of the relationship can be either positive. So here, this is a scatter chart. This is the regression line. So this is basically the trend line in the regression, in the scatter chart. The trend line in the scatter chart uses the least squared method. It's a line. And then the equation is actually the equation that you should get using the least squared method. So when you have a positive linear relationship, it means as x increases, y also increases, which means the slope is positive. B1 is positive. So in your linear equation, if the slope is positive, it means that you have a positive relationship. If the slope is negative, it means you have a negative relationship, meaning x increases, y decreases. So they have an opposite relationship. If the slope is 0, it means that there is no linear relationship between x and y. We can't comment really on the nonlinear. We may have some nonlinear relationship and you still get a basically a slope of 0, which would only indicate that there is no linear relationship between x and y, all right? So when there is no linear relationship, you get a flat line. When you draw the linear trend line, you would get a flat horizontal line, which would basically says that y doesn't change. If you increase or decrease x, y doesn't change, or at least the estimated value for y does not change. So that is the conclusion that we make. Before I go ahead and go through the example, the Butler example, I'd like to talk about very briefly about the least squared method that we're going to use. I'm not really going to go over the details of it. it really doesn't matter. But what is important here is that you need to understand that this is a technique that we use for finding the estimated linear equation. And that just uses the sum of error from the sum of error, basically sum of squares of error. It just tries to minimize that, and by minimizing the sum of error squares, it just finds B0 and B1. So that's just what you need to understand. It just tries to minimize the sum of squared errors. And error is y minus y hat. Y, the actual value of dependent variable, minus y hat being the estimated value. All right. So now I'm going to go ahead and go to the Excel file. Now we want to see how we can find the linear equation when we're dealing with simple regression. So this is a case of simple regression because we are using one independent variable to explain our dependent variable. So this is the data file is Butler. In this data file, we are going to predict the time, the travel time, based on the distance of travel, based on the length of travel, the miles that the driver has to travel. So, this is a trucking company example. They want to understand how long it should take for a travel, beforehand, before sending out the driver. So in this example, we are using the length of the travel, the mileage, in order to estimate the time. It's very important for the company to have a prediction of the time that it takes in order to be able to control the driver, right? So the number of assignment doesn't really matter. So that's just the order. That's just nothing. It's we want to predict the time. So this is my dependent variable. This is the one that we want to predict, and miles is the one that we're going to use to make prediction. We're going to use miles to predict the time. So independent variable, dependent variable. All right. So now, when we're dealing with simple regression, we can first visualize the relationship by a scatter chart. Just going to add a scatter chart. So this is Butler Trucking Company, time versus miles. And then I'm just going to add axis titles, and I'm going to get rid of the grid lines. So this is the time that it takes, time, and it's actually in hours. And then miles. All right, so now I have, I see the relationship between, so this is just a scatter chart. A simple scatter chart just puts the dot for each one of these rows. For each assignment, we have one dot on these scatter chart, all right? Now, if we just do the trend line, the linear trend line, it gives us the estimated linear. So that actually if you add the trend line here, that would be the linear equation. If you get the equation on this, if you display equation on chart, that equation that I'm gonna make it a little larger. All right, so this is the linear equation, except that this should be y hat. Y hat equals slope times x, x being the miles, number of miles, plus 1.27. So this is the y-intercept, this is the slope, and this is the, y hat, the time, all right? So that would be the equation for this line. All right, so this is one way to get this. This is one way to get the linear equation. The second way that you can use to get this equation is through a data analysis tool pack. So I'm gonna go ahead and quickly do that, but we also need to make interpretation of these coefficients. Let me just quickly get this equation using the data analysis and we get back to this. We get back to the interpretation. So for getting the equation using the data analysis tool pack, you need to go to Data tab, Data Analysis, and then call the regression tool. So just call regression tool and then input Y range. So we have one input tab and one output tab and one tab for residuals and one for normal probability. We're not going to be dealing with normal probability. We're going to be dealing with residual plots later on. But for now, just go ahead and put, for just getting the equation, you can just put the Y range. Y range would be the variable, the dependent variable, the variable that you want to explain. So that would be always one column. X can be one or multiple columns. In this case, this is a simple regression, so I'm just going to put miles. Since I started from the first row, and in my first row, I have, for both cases, for X and Y, C1 and B1, they're both labels, they're both numerical values. So I just check labels. If you start from C2 and B2, you don't need to check labels. But since I started from text cells, I need to make sure that those are identified as labels. Otherwise, you're going to get error message. So constant, so nothing else. I'm not going to really be touching any of these. So I'm just going to put it in the same sheet again. For now, I just need to get the equation. So just press OK. And then once you press OK, Excel provides you with 3 tables. So summary output for the regression provides you with regression statistic, some ANOVA analysis, and then the coefficient, the actual equation, and some statistical inference, some statistics for statistical inference and hypothesis testing. But for now, just we're trying to get the equation, and what matters here is just this part. At the third table, the coefficient, just highlight that. I'm just gonna highlight this. This is gonna be the part that we need to know right now just for getting the equation. So I have the coefficients. I have the intercept and I have the coefficient for miles. So always the first step is writing down the coefficient, the linear equation. So what it was that we tried to explain, we tried to predict, it was time, travel time. It's equal to y-intercept 1.22 274. So that's the intercept plus the coefficient for miles times miles. So the coefficient would be 0.068, just round it, times miles. So that is the equation, and that is exactly the same as what we got using, that's exactly the same. I just rounded with 3 decimals, but in this graph, we have it with 4 decimals, but that's just exactly the same. They're supposed to give you exactly the same line. Now, this is the equation. Now, if I ask you to make a prediction for a travel with 100 miles, so we have it, travel with 100 miles. What would be your prediction? What is your prediction? So that's the first thing that you need to be able to do, making a prediction, basically using this line. So if the travel is 100 miles, we just need to plug in 100 into this equation. So the time would be time for this specific travel, or estimated time. Estimated time would be 1.274 plus 0.068 times 100 miles. All right. And that would be 6.8 plus 6.8 plus 1.2, that would be 8.074 hours. So I just plugged in the number of the distance or the length of the travel into this equation, and that will give me the estimated time of the travel. All right, so this is how we use it. But now, another part of this interpretation would be just understanding of the meaning of this the coefficient. So what is the meaning of this, the intercept? Intercept is y-intercept is the value, the estimated value. Intercept is actually B0 in our equation. That's the estimated value of time or dependent variable if miles, if the independent variable is 0. Estimated value of time if miles is 0, and then slope B1. The interpretation of the slope is the change in the actual change in time or dependent variable if your dependent variable increase by 1 unit. And unit here is is 1 mile here. So if the distance, if the length of the travel increases by 1 mile, how much your time increases? So this is how we interpret that. So here, the slope, I'm gonna go with the slope first, and we talk about the intercept in a minute. So slope here is 0.068 hours per mile, or alternatively, almost 4 minutes. All right, so if you just multiply this by 60, so each hour has 60 minutes in it. So if you just multiply this with 60, it would be almost 4 minutes. So the change in time if miles increase by 1 unit. So if you have a travel of 100 miles, this is gonna be the time that it takes. But then if you have another travel with 101 mile, it's gonna take this much time plus the slope, 8.074 hours plus 0.068 hours. So each additional mile would take 0.068 hours or almost 4 minutes. So I'm just gonna write it here. Each additional mile of travel will take, I mean, we're talking about estimated values here, all right? Should take estimatedly 0.068 hours, which is equivalent to almost 4 minutes. All right, so that's how we interpret this. Each additional mile of travel will take this much, equal to the slope of time, right? So that's for slope. And then for intercept, here in this case, intercept is significantly greater than 0. So we are saying by this definition, the estimated value of time if miles is 0. So basically, if you don't travel at all, it's gonna take 1.27 hours. All right, 1.27 hours it's gonna take even if you don't travel. So that doesn't make sense. That doesn't make a lot of sense. So just think about it. Why? I mean, logically, in this example, B0 should be 0. Why? Because if you don't travel, if the length of the travel is 0, then the travel time should also be 0. But why isn't it the case? Just think about that for a second. The reason is because we may have other factors that are not included in this regression. We may have, let's say, the number of assignments, the number of deliveries that they're gonna, the number of basically parcels, for example, that they're gonna deliver to the different customers, right? So that also takes some time that we don't have it here. All right, so that would that may also be contribute to this large B0 y-intercept that logically should be 0, and it's not the case. It's actually a significantly positive number, which we don't like it, right? So that seems not to be true. And so that's one reason. So we may have other factors that are not included in this model, but it's very important to understand that this model, so one reason is because other variables other than miles affect time. The second reason is the notion of experimental region. So we have actually 0 is outside of experimental range. So we have a concept, experimental range. Experimental range is the range of independent variable that we are using to make prediction. So the range of X, the range of miles is between 50 and 100. 50 here and 100, minimum and maximum of X. So this model that we've built here is only useful, is only helpful if you are going to make predictions between these values, between 50 and 100. If you want to make prediction outside of these values, it's going to be risky. Like, but again, other things can come to the picture, right? So you may have a nonlinear relationship. If you go a little bit below 40, right? You may have again another nonlinear if you go a little bit above 100. So the shape of the relationship may change if you go outside of your experimental region. This value, the intercept, is the best value that makes your model work well within the experimental region. Now, this intercept itself, if you want to predict, if you want to interpret the intercept in this way, the estimated value of time, if miles is 0, that means you are extrapolating, which is basically extending the equation for outside, for making prediction outside of your experimental region. And you're extending it too much, 50 units to the left, right? So miles, the minimum of your miles that you included in your model is 50, and by just looking at this number as the time, if miles is 0, you're going outside of your experimental region to the left side for 50 miles, and that's too much of extrapolation. So that's another reason. If you had travels with 0 mileage or numbers close to 0, then that should be a much more logical number.